Hi, welcome to this lesson on Euclidean geometry, ratios and proportions. Let's have a look at question 6. We're given a trapezium ABCD with the side lengths AD, AB and BC all equal to each other, and angle ADC is equal to angle BCD. So that's all the given information to us. Okay, so there's a lot to go off there. First of all, because it's a trapezium, we know that two opposite sides must be parallel. In this case, AB is parallel to DC in this figure. We're also given three equal lengths here, and I've noticed two triangles. Triangle ABD, right, which is this one here. Okay, and then triangle ABC, which is this triangle here. Notice those two triangles are isosceles triangles. So they're both isosceles triangles because we have AD equals AB in that triangle ABD and AB equals BC in triangle ABC. So therefore, if I label these angles as follows, I'm just going to call them 1, 2s over here. Then let's start off with the proof that we are looking for. We're showing that BD bisects angle D. So what we want to show, so proof. So to show that angle D1 equals angle D2, that's what we want to show, because therefore line BD will bisect that angle D. Okay, so firstly, I want to observe the following. So in triangle ABD, we have AB equals to AD. So this implies that this is an isosceles triangle. Okay, and that further implies that angle B1 equals angle D1. Okay, so these two angles here are equal because of the isosceles triangle. AB is equal to AD. Next, I want to notice that because line AB is parallel to line DC, we have angle B1 equals to angle D2. And that's because AB is parallel to DC because it's a trapezium, and therefore alternate angles are equal. So B1 equals D2. Alright, so what have we shown? If B1 equals D2 and B1 equals D1, therefore angle D1 must be the same as angle D2. But that's exactly what we wanted to prove. We wanted to show that the line BD bisects that angle D. Alright, so that is how we would prove that the line BD bisects the angle D. We relied on the fact that triangle ABD is isosceles, so these two angles were equal, B1 and D1, and we also used the fact that because BD here is a transversal line between the two parallel lines AB and DC, that angle B1 and angle D2 are equal by alternate angles. Next, you want to prove that the two diagonals are equal in length. So what are we required to prove here? RTP, that the diagonal AC equals the diagonal BD. Okay, so let's try and write out a proof. So whenever you're trying to show that two side lengths in two different triangles are equal, and you don't necessarily know that they're right angle triangles, because we could just use Pythag and work out the hypotenuse or the adjacent sides. Because we don't know if they are 90-degree angles, the general methodology of showing that two sides are equal in triangles, okay, is to show that there are two triangles that are congruent to each other. And by congruency, all corresponding angles of two triangles are equal, and all corresponding side lengths are equal as well. So let's look, where is AC and BD in two triangles that have information? Okay, so I'm going to look at triangle, I would say ADC and BCD. The reason for that is because I was given that these two angles are equal. So that might help us. So I think as a criteria, we might try to show that all corresponding angles are equal in the two triangles. Therefore, we could have a similarity, but we don't want similarity, we want congruency. So I wouldn't then necessarily use angle, 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 because that's similarity. So I would need to use one of the four congruency conditions. All right, so let's recall the four congruency conditions. You either need a right angle, a hypotenuse, and a common side. We don't have a right angle at all, so we can't really use that one. We could show that all sides are equal, but again, we're actually trying to show that one or two sides are equal, so we couldn't necessarily use this one. We could try use side, angle, side, right? Or angle, angle, side. So possibly one of these two might be the way to go. Okay, so I'm going to look at two triangles that have AC and BD in their length. So I'm going to say consider triangle ADC, because that's got the length AC in it and it's got this angle D here. And I'm going to consider triangle, let's say BCD. Okay. Or triangle ADC and triangle BCD. Yeah. All right. So let's pull out those triangles and visualize what's going on here. Okay, so here's A, here's D with a known angle, and here's C. And then we have triangle BCD, which is this one here. Okay, BCD. Now we know that AD and BC are equal, so that's important. And we know that this angle here, angle C here is equal to angle D here. We were given that information. And notice that they both share a common side, DC. Now look at this. We've got an angle that's included between two side lengths that are equal. So therefore, I can say that AD equals BC, that was given. Okay. I can say that DC equals itself. That's a common length. Okay, so a common side. And then lastly, we're given that angle ADC is equal to angle BCD. And again, this was given to us. So by these three criteria here, we've shown, therefore, that triangle ADC is congruent to triangle BCD in that exact order. Okay, it's got to go in that exact order. You can see from B to C and A to D, it's that same side length. Then they meet the same angle, and then they go to another equal side length. So that's why we say they're congruent by side, angle, side. Okay, so in terms of the sides, it's from BC and AD to the angle D and C, and then the common side DC each. Now, because these are congruent, therefore that means that if I've taken the order AC, then that must be equal to this order here, BD. So therefore, AC equals BD, and that's exactly what we wanted to prove. Okay, so the way you read off congruencies and similarities in triangles is really important. Like, for example, DC, that would equal to CD, which is exactly true, right? It's the same side length. You can also say that here, AD equals BC, and that was given to us, so that's true. Okay, so the way you write out your congruencies and similarities needs to be in the exact correct order for it to make sense. Lastly, they tell us if the ratio of the side length DC to AB is 5:4. Okay, so essentially what that means is that if you take DC divided by AB, that's 5/4. And I can rewrite that, for example, as 5K/4K. Okay, because that simplifies down. So therefore DC, if that's 5K units, then this is 4K units. Then we want to show that the area of the trapezium ABCD is 2.25 times the area of triangle ABC. Okay, so we know we need to use triangle ABC. And notice because I wrote AB as 4K, this side is 4K units and that side's 4K units as well. All right, so let's see how we can go about this. Well, if we look at triangle ABC, all right, I can see that if I want to find the area of that, I would need a perpendicular height. All right, so the perpendicular height in triangle ABC here is exactly the same perpendicular height of the trapezium. So I can call that common perpendicular height H. So firstly, what I want to note is that the area of triangle ABC, that's going to be a half times the base. In this case, the base here is AB, so 4K, times the perpendicular height H. Okay, so that is the area of triangle ABC. Now, what is the area of triangle ABC? So what's the area of triangle of trapezium ABCD? Okay, so let's work that out. So the area of the trapezium ABCD, we know that from the formula for area of a trapezium, it's half times the sum of the two bases, AB and DC, times that same perpendicular height H. Okay, but we know that AB is 4K and DC is 9K. Okay, times the perpendicular height H. All right, so I can simplify that. 4k plus 9k, that's 13k times h. All right, so now I've got an expression for this area of the trapezium, and I've got an expression for the area of triangle ABC. Okay, so this essentially becomes 13 over 2 times k times h. But on the right-hand side, 2.25 times the area of triangle ABC, that is 2.25, so that's 2 1/4, right, times that area of triangle ABC. But 2 1/4 is 8 plus 1 is 9, so that's 9/4, times the area of triangle ABC, which is this area here, a half times 4k times h. So let's see what happens here. So the 4's will cancel. All right. Okay, I've just realized here very quickly that that's not 9k, right? So what is that? So let's just get our blue pen out here. So I'm meant to write DC, that's 5k. That's better, right? So 4k plus 5k is 9k. So it becomes 9 over 2k times h. I quickly spotted that because as I'm doing the red triangle, you can see the areas weren't going to match up, right? Okay, so now 4 divides into 4 and you're left with 9 over 2 times k times h. So now look at that. We've shown equality. So therefore the area of trapezium ABCD is exactly 2.25 times the area of triangle ABC. And we've successfully proven that equality. All right, so that's how we would do this type of question using proportionality and the properties of a trapezium. I'll see you in the next one.